why this thing is important. The reason kind of being that, flying elephant is one of these things which is usually considered as like an example of thing you say to mean something is impossible. Like you probably have friends saying, I will come to Mars Society the day elephants fly.
Who said that?
This guy on the street. Actually, I just probably didn't say that. And that is not really that quite obvious. And of course, like, I don't know, 10 years ago, 5 years ago, if someone asked me a question, why can't elephants fly? I would say something like, oh, because they're really heavy or really big. But the more I kind of got into it, the more I realized that it seems like the whole nature is fine-tuned to disallow elephants flying. Like, it's almost there, that's what I'm trying to convince you about, but it kind of knows that we want to try and make elephants fly, and it tries to stop us there. So, a lot of people felt that way throughout history, that it's not that obvious that elephants can't fly. And it was really only first voiced by Walt Disney in 1941 production of Dumbo, which I very much recommend everyone see. So it is literally what it is. It identifies the current state of affairs, which is people think that, or birds think that elephants can't fly, and convinces them otherwise. Unfortunately, the whole film was like, at the time, it was misunderstood. I mean, critics from big mainstream media treat it as a kind of metaphor of human life, instead of its direct meaning, which is that maybe elephants can fly, and this topic has been on a bit of an elephant in the room ever since. And it was until 2005, I think, when Black Eyed Peas released their album Elephant, which featured very clearly lines like "Fly away now" or "Fly away now." It's actually not the same one; it's just repeated song. "Fly away now," and then obviously the main one: "I'll be falling up, never falling down, because I spread my wings and fly up." And this is actually not like how I first got into the topic. So my personal story. This is an album by White Stripes and it's the first album I bought myself for my own money. I listened to it over and over again in my room, and it was great. But like one thing I couldn't get out of my head is, why is the album called The Elephant? Because it features no songs that are called Elephants. Elephants don't feature at all in the whole thing, and it really took me quite some time before I realized that the elephant has already flown away. So I went to research a topic. This is me with a president of the Elephant Institute in South Africa. It's really neat. I used to have long hair. And I spent some time researching at the time biomechanical properties of elephants. But I really then realized that I should really get on to more the mathematics of it, because when we consider individual designs try and make elephants fly, it's really we can miss things. And my approach, which I'll apply to you today, is kind of more rigorous and sort of making sure we define everything properly and don't miss anything. If you think about it, defining a flight is not an obvious thing. So, is that a flying pen? Well, not really. It's a falling pen. We need some kind of definition that will be pretty general, but still define what we mean by flight. Let me just define a flight. So definition 1. So what are the essential components for elephant flight? So first of all, we need elephant, another E here, that's alive. I'll try to on this point. There are many designs which will try to in a way, which will be kind of for dead elephants flying, or say flying through plasma, super hot elephant dies. We don't want that. So obviously, no equipment. I will define the word equipment later. By which I mean I won't, but I make you think I will, so forces in balance, I'll show the force in a minute. Balance. And finally, glide angle, which I also define, but I will actually, less than 45 degrees. So how is this going to work? Do we have like an elephant? And it's flying through the sky. It's got some velocity in some direction. And the force on the gravity, the drag force, drag, and the lift. Now, we want, and this is our glide angle, alpha. So, you can see where the distinction between gliding and falling comes around. So if we draw like a elephant face space diagram, actually we can forget about this part going up. So we effectively make a truncated diagram. This corresponds to falling, and this is flying. So if it glides more, this is more falling than flying. This is more flying than falling. More falling than flying. It actually makes sense. And from that we get some like conditions we should have for this glide. So we want the resultant of these two forces, to exactly counteract gravity. For all the forces to be in balance. That's kind of our definition of flight. So this implies two things. I can leave it an exercise, but like, check. First of all, lift force must be at least as big as drag force. Drag force. And secondly, the force must be greater than half gravity force. These are all magnitudes. These are not sufficient conditions, but they are necessary conditions, and they're pretty sufficient as well. So we need to know about the mechanics of lift and drag, which brings us to the two-dimensional flow. And we say it's incompressible. One way I would say it's incompressible, which means that you can't compress fluid, and it's irrotational. So there are no like weird things whirling around. That's just a simple theory. It doesn't really work, but it works to a good approximation very often. And those two conditions are expressed by those two equations. The gradient of the velocity field is 0, and the curl of the velocity field is 0. Now, I know not all of you can know what these things mean, but this is basically rotation, swirl, and this is divergence, saying no divergence, there are no sinks of things. Right? Fran understands. Ask Fran if you don't understand. And this gives us a very interesting insight if you know something about, who here knows something about complex analysis? Yeah, you don't understand about it. So the idea is that instead of considering elephants in real space, we consider them in complex space. That makes things a little simpler. And here is the reason why. If we define two functions, phi and psi, then to be the following. So we have some velocity field, x, y. At each point there is some velocity with components ux and uy. And if we define our function psi such that ux is d phi by dx, the partial derivatives, which are like derivatives. And this will be, well, let me change to psi, actually. dx psi by dy. Actually, let's do it fine. Then the condition gradient u equals 0 is automatically satisfied. You can check that, it's really easy. Similarly, if we define the other function, psi, the other way around, so ux is dx psi by dy, and uy is dx psi by dx, with a minus, we're going to end up, actually, let's the minus in here. Yeah. We're going to end up with this condition being...
Why is the gradient 0? The divergence 0, sorry.
So...
Shouldn't the curl be 0 in that case?
Yes, obviously. Thanks. Yeah, no, very nice, very nice. But this will give us the zero diverge because of the minus. Yeah. Who said that? Thanks. And so, but that's kind of just like the details of it. The reason I'm doing it is for the people who know something about complex analysis. What we end up with is that d phi by dx, which is ux, is d phi by dy, right, from there, and d phi by dy equals uy equals minus d phi by dx. So, does anyone recognize these equations? Sorry? Yeah, they're Cauchy-Riemann equations. Which basically is saying, Riemann, what? Which basically is saying that if we take a function, a complex number, which is phi plus I psi, it's an analytic function in a complex plane. So here is the intuition for those of you who don't know what it means. So things can be defined in terms of complex numbers, but they are not always nicely defined. So nice functions, it turns out that all of the nice functions in complex plane need to satisfy these two conditions, which is basically saying that, because if you imagine like a complex plane, like it's like any two-dimensional plane, if you like consider a point and see how the derivatives at this point work, we want the derivatives to change smoothly as we rotate around. Otherwise it's kind of like bumpy and stuff. So all the nice functions in the physical sense need to satisfy these conditions. And so what that means is that all the nice functions on complex plane automatically describe fluid flows. So you, like by themselves. So it's the most natural way of doing fluid mechanics is by working out, by working in complex plane. So there is this joke about like with this, I mean it's not, I'm not going to say a joke, don't prepare it for blind, but it's a thing people say that like physicists consider models of spherical cows and stuff and ha ha ha. And they don't. I mean you can convince yourself that a spherical elephant can't fly. I mean unless it's spinning, but then it needs to be spinning very fast so it will be dead, so fly. But we're going to consider, there's, each function of complex plane can describe a fluid flow, but it can also describe a transformation from one complex, from one set of complex variables to another one. And it turns out that if we take, I'm just going to say what the strategy is. So here's how people approach the subject of elephant flight for ages, which is step one: solve for sphere. So solve the problem of fluid flow around a sphere, or a circle in two-dimensional case. And then, two, do a conformal map, sphere to elephant. So we write down a function that distorts this sphere and makes it into an elephant. And because everything is nice, our solution, we can just use the same function that we apply to the elephant, we apply it to the fluid flow, and this automatically is a fluid flow around elephant. So, solve for elephant, or like, solve for elephant. And that has really been the mainstream research for many years, but obviously it's still actually an open problem, how to do a general mapping between a sphere and an elephant. There has been a partial progress with horses, but the problem is like where when you have the what they call the tusks. The tusks have very pointy edges, and they create a singularity here, which is very difficult to do. But for our purposes, we can make a model elephant, not a sphere. So our model, the Kuta-Zhukovsky model, which I referred to, is a sphere with ears. And you can argue that only ears contribute to lift because the rest is just contributes to the drag. So we just need to work out the flow around ears. And it's actually quite simple. The function we're going to use is the transformation big Z equals small z, previous coordinates, z stands for a complex number, times c squared, the speed of light, no, it's just a constant, plus z. And you can convince yourself that what it does to a circle, which has c here, has a bigger than c, it converts it into an ellipse with focal points at c and c, where the length of this axis is defined by a, so it's a c squared, where a is the original radius of the sphere. And so, obviously, the ears are like plates. So what we need to do is take c equal to a, and that will distort our whole sphere into a flat space. For those of you who like to actually know something more about it, we actually have to also care about removing singularities in here, and that gives us the lift. So, if you all do all of that, and I've done that, that can take me a long time, but you don't need to do it, you can just trust me. Or I can give you some good references, there's plenty of excellent books on the subject. We end up with lift is equal 4 pi rho density of air, u squared, the speed of incident air, sine squared alpha, and then the length, the two lengths of the wing. So this is A, and the other one is L. And I don't really want to bore you with calculations, but for a typical African elephant, what we end up with is the lift equal to 6 u squared, where u is in meters per second. And I think that's pretty interesting. Because one of the first things people say why elephants can't fly is because they're too heavy. But if you try and make that, so we said that one of the conditions is that it needs to be bigger than half of the mass of elephant. If we try to solve that, we get u equal to about 100 meters per second, which is not that fast. I mean, it's pretty fast, but it's like if you have a cannon, it's pretty doable. So, it's not like elephants don't fly because they're too heavy. Because if they just get quick enough, they can actually fly up. I mean, for certain elephants, this could be as good as 10. Like you have a particularly well-shaped species. So that's one of the core misconceptions. So what breaks down? Well, the problem is the drag. So our theory actually doesn't predict any drag on this sphere. And it's all perfectly symmetric. Now that's not what happens in real life. The flow around the sphere gets really weird. So the sphere is like the body of an elephant. It's the main part contributing to the thing. And we can actually write down that the drag force is to some good approximation proportional to, the square length, the square of speed, rho u squared, speed of sound, minus some small correction for the trunk and everything, which is a higher order, higher than u. We don't know this constant very well, but it's something of order of 10 to minus 8. Now, what this means, if you try and plot, so we want the lift to be bigger than drag. And what this means is that if we plot the forces on one graph, this is the lift, this is the drag, but then the u cubed bit starts kicking in. And we can actually intersect those two things. And we can find a place where they can fly. Well, it turns out actually there is a small problem with that, which was very unexpected. It's only recently discovered. So the speeds we're talking about here, this is about 10 to 8 meters per second. Which, as some of you may know, is about 1/3 the speed of light. Now, what happens to an elephant under relativistic transformation? So, as the elephant goes faster and faster. Lorentz contraction means it gets squashed, so it becomes something like more of that sort. So the body gets squashed, and the ears also get squashed. But look, the drag does not depend on this length, it only depends on this radius. But the lift actually does depend on A. So as we go to relativistic speeds, so Lorentz contraction, is that what I meant? Yeah, so there's a prediction of special relativity that as you move very fast, your length in the direction you're moving into changes from something to something times 1 minus your current speed, some correction due to the speed of light. That only becomes relevant if you are close to the speed of light. So it's actually something like your speed minus your current, so it's like your current length, 1 minus d squared over c squared, say, to some good approximation. And if we plug those into our equations, this gives you u to the 4 correction in the lift with some constant, which means that lift, when it's about to intersect the drag, it flies off, and it never does. And this is one of the typical examples of what I mean when the nature is fine-tuned, not to allow elephant flight to happen. Like, you're almost there. If this wasn't 10 to 8, it was at 10 to 7, we'll be perfectly fine. But it's not. And that's one of the big problems with our world. So, when people realized that, they started, of course, that's not the only way that you can make elephants fly. And one of the particularly tempting designs is to make an elephant into a hot air balloon. Of course, you can't make it hot, because then the elephant, we can't make it too cold either, because elephants are quite used to warm temperatures. So is everyone familiar how hot air balloons work? Kind of. So, can you, I'll say it anyway, because there's a simple way of understanding what exactly the force is. So, there's your air, and imagine there's a parcel of air here, which weighs something like m, or we say density of air times its volume. And this parcel is in balance, so that means that all of the air in the world is pushing it down with weight. It's pushing it up with its weight, and then this is balanced exactly by its weight, and this thing is in balance. Now, if you replace this parcel of air and place an elephant here, the air outside doesn't know that what is inside an elephant, not a parcel of air. So it still exerts the same force. So even though this force changes, the buoyancy force from the air outside stays the same, is equal to the mass of displaced air. So that's the reasoning behind it. Okay, so so what we really need is to evacuate the elephant, and hopefully this weight will be large enough to counterbalance its mass, which is about 5.5 tons times gravitational constant. So we need to, obviously we can't modify the volume of an elephant, so we need to make density really large. So any ideas for how to make density really large?
Make the balloon bigger.
We can use a high pressure environment, but yeah, actually let's do that. So we need to be kind of considerate about
the elephant's safety.
No, I don't want the high pressure environment because it may implode the elephant from the inside. But we can do cold environment, like in the last instance, as long as the pressure stays alright. We can give it a coat or something. So if you can use the ideal gas equation, which is that the density is equal to pressure of air times mass of an individual particle divided by some constant times the temperature. So I wouldn't modify the pressure, air is air. So we're left with a temperature to modify. So if we calculate what is the rho times v for a typical elephant equals mg, guess what we get? And you guess this for what kind of temperature we need. So another way to, we might make the gas heavy by making it really cold.
Minus 200.
Minus
Celsius.
200 what?
Celsius.
Close, close. Can we please work in kelvins, like, or
10.
Fahrenheit?
3.
0.2.
3.
Is it 3? Very good, Fabian. It's actually 0.6. And when I think it was Koshi who first realized this, and people were very happy at the time because this gave like a good. There wasn't technology to achieve this temperature yet, but there was a prospect, and this prospect completely smashed with quantum mechanics coming in. So think about this. What happens with this temperature? Well, if you imagine the individual gas particles, the typical distance between them. So you can imagine the number density, which is the number of particles per unit volume. Then to get the typical distance between two particles, we say it's approximately n to minus a third. The reason is that in a volume V, there will be n times 4 times like r cubed for the volume of a sphere. So r cubed gives you n to minus 1, and it cancels this n, and everything works, except for the constants here. So this is the typical distance between two particles. And we can also calculate their temperature. So like, we know the temperature, which kind of corresponds to how quickly they move around. That gives us the speed, which is a typical speed of a particle, which is approximately equal to root of k dt. And we can get momentum by multiplying it by a typical particle mass. And guess what we get when we multiply p times r? We get about 3/4 of Planck's constant. Now, there is this theorem in physics called the Schrödinger-Heisenberg uncertainty principle, which says that if for any particle, if you multiply its momentum by its position uncertainty, it must be at least equal to h bar. So it's just about there, but it's not. It's just slightly too cold, so that quantum mechanics forbids this gas from existing as it is. And we need to use a completely different theory. And believe me, the other theory doesn't work as well. Another thing I don't have time to consider was changing the mass of the particle, of the air. So instead of putting it inside like oxygen, putting it in some chemically engineered compound that will lift it up. And guess what happened? The elephant particles, which are the theorized particles for a stable animal, are just slightly heavier than is allowed by this so-called semi-empirical mass formula. So if we consider a nuclei composed of protons and neutrons, it's held together by a strong force, but they kind of try and get away because some of them are charged, and two charges try and get away. And it turns out that the limit, the maximum stable size of this molecule is about 250 protons, and an elephant particle, of course, is about 350 mass of protons. So it really is. It's really we're almost there, but not quite. Yeah, there's other thing. I don't really have time. I'll just skip through some stuff. There are different things you can get out of this talk. I think the first lesson is conformal mappings. Like, I don't have time to go over it, but study conformal mappings. So conformal mappings are present everywhere. They present angles between transformations. So they're present in like design, in computer design. Apparently they're present in neuroscience when you try and map the brain, decide how to best map the connections of something, and you want to preserve angles because apparently that's important, right? The second part is, despite some people claiming this talk being ironic, I really, really do love elephants. And They're amazing species, but they're dying really quickly. Over the last 50 years, the population of elephants has decreased by over half. And it's kind of self-prospected, like our children or grandchildren will be living in a world where elephants can be like mammoths, they can be like an ancient thing that apparently used to exist back in the day. And its main threats to elephants' life are poaching and global warming. And I think we should tackle both of these issues. But poaching is just so completely ridiculous, and it still exists, and apparently it's kicking off again. And so if you feel like you like the elephant bits of the talk, then go and support the elephants, wear elephant hats and stuff. No, there's actually an organization that sells elephant hats and protects elephants for the money they earn.
What's the elephant hat made of? Elephant?
No. Oh man. No, don't wear elephant hats that are made of elephants. And finally, if you like the fly part of the talk, then there's a great club in Oxford called the Oxford University Gliding Club, which I happen to be part of. And
Maciek, I think we should end this talk soon.
yeah, this is the last slide actually.
Okay, that's
I
fine.
can spend like 10 minutes. So yeah, flying is really great. And elephants can't fly yet, but you can. Just tell me if you want to, and we'll go up to the airfield, which is just outside of Oxford, and put you in a glider and instructor, and it's absolutely awesome, and I absolutely love it, and everyone who went here loves it, Albert loves it, Leslie loves it. Yeah. And yeah, that's it. If you have any questions,
Then ask him afterwards.
happy to address them now.
Yeah, guys, I'm really sorry that included physics. I didn't vet the talk. I know this is supposed to be a set of maths talks.
Well, it was Kit who wrote down, who said this and said like these two particles are effectively at infinity.
Yeah, that was.
It's actually what we do in physics. If it's like more than a meter, then they're effectively.
That was borderline. If anyone feels that their personal views have been challenged, then talk to me afterwards.
Okay.